I'm going to go ahead and finish up our nuclear physics. We're going to go over something called Rutherford scattering. And basically in this, you have a bit of gold foil, and you send some high energy electrons at it, an electron beam at it, and then these electron beams in this thin little beam, they diffract. And since we know now that, or think now that matter even travels in waves, then these electrons with their de Broglie wavelength will create an interference pattern as they diffract to this, kind of like the diffraction grating that we had talked about before. So what will happen is you'll get a maximum, towards the middle, and then it'll go off to other little things like that and trail out. And so what you're interested in looking at here is, one, the angle to the first minimum. That angle, I didn't draw that very big, but we'll call it theta. All right, it's that little angle right there. And very similar to our result before, you get that sine of theta. So I'm not going to go through all this kind of stuff before because we've done it in the past. Is equal to the wavelength over what ultimately is the diameter of the nucleus. So if this is something like gold foil here, what you can do is you essentially have a single gold nucleus coming in, and you have all the electrons coming in as a wave, right? And they're diffracting around the edges of this gold nucleus, and then they're overlapping, and you're getting this whole interference pattern over here, right? From this, like the single slit like the single slit problem that we did before, but with visible light. Now we're doing it with electrons. They create an interference pattern too when they're sent through slits. So you get this interference pattern very similar to here. Theta is angle to first minimum, and d then is going to be the diameter. Is the diameter of the nucleus of gold, what's diffracting it, okay? This isn't including all the empty space. This is about the nucleus itself. And so if we can start to figure out what the size of this gold one is, then you can do some basic geometry and math and figure out that the radius of other nucleons can be kind of done like this. So like this would be like the example of, if I know I can fit 50 golf balls inside a box, and then what happens if I double the size of the box or triple the size of the box? Should I then be able to figure out how many golf balls I could fit in there based on how many fit in the smaller box? And so if we think along those lines, we can say then, this was a good equation. You can say then that the radius of a nucleus, so this is the size of nucleus, right? Size of a nucleus, that's what's Rutherford scattering, is r, the radius of that nucleus, is equal to the radius of a single nucleon, okay, which is pretty small, times the number of nucleons cube rooted. Okay, so A is number of nucleons, and R naught is radius of a single nucleon. And that's something on the order of the magnitude of 10 to the negative 15th meters. Pretty small. But at this point, this is weird. Now, think about this 1/3. This comes from how you pack spheres together. Spheres can pack in not just like cubes, but you can have spheres that pack close packing kind of thing, where they get down in between each other a little bit. And so if you go through the geometry and all this, you can see where this 1/3 comes from, but it's not super important to understand the geometry of this. Just know that in this kind of close packing, you'll end up getting that kind of relationship. And so that's a pretty good one to keep in mind. And then from there, we can then talk about the density of the nucleus. So density, of course, is just mass, and this would be the total mass over uh, over the total volume, right? Total volume of the nucleus. And we can actually replace this by changing it to uh, we can go to mass of the nucleon times the number of nucleons to get that over the volume instead. Okay, so we can replace the total mass of the nucleus with just look at the mass of a single nucleon times however many there were, and basically you would get the density of it. Okay, so you can find places where they'll tell you the densities of these nucleons for different ones, but anyway, there it is. That's the basic way of calculating it. Okay, that's pretty much all for this little short video. I'll continue the next one after this in a different video because it's gonna be a little bit longer. All right.